All right, example 8. Determine all local extrema. So again, analyze the critical points, essentially. So we've got our function x ln x. So the derivative of x ln x is derivative of the first times the second left alone plus the first left alone times the derivative of the second. So this should be ln x plus 1. That's our derivative. So if our derivative is that, then we want to check to see when this does not exist. Well, the domain for this function is all positive numbers because of the natural log of x's domain is all positive numbers. And here, the domain of this is again all positive numbers, so there's nothing that is excluded from this function's domain that is included in this function's domain, which means the derivative of this function exists everywhere this function is defined. So I'm going to say it exists. There's nothing to check there. So that means we do have to check and see where the natural log of x plus 1 equals 0. Well, when does the natural log of x equal negative 1? Well, this would be at x equals e to the negative 1. Or x equals 1 over e. So, take our number line, negative infinity to infinity. List our first derivative. Label our critical point. And that the first derivative is 0 at that location. So now we have to pick sample points. So we can pick, well, we have to pick something that's bigger than 0 but smaller than 1 over e. How about I pick 1 over e squared? What's the derivative at e to the negative 2? Well, the derivative at e to the negative 2 is negative 2 plus 1, which is negative. What about here? I can definitely pick x equals 1. The first derivative at 1 is the natural log of 1, which is 0, right? ln of 1 plus 1. This is 0. So 1 is bigger than 0. So this is positive. So what we know now is that there is a local minimum at x equals 1 over e. And that's it. So local minimum at x equals 1 over e. Example 9, example 9, determine all local extrema for this function. So f prime of x, we'll use the quotient rule here. Derivative of the top times the bottom left alone minus the top times the derivative of the bottom all over the bottom squared. Now, this derivative, we can't divide by 0 because no real number squared plus 3 equals 0. So I'm going to say exists. Nothing to check there. So we do have to set this equal to 0. Now the only way that a fraction is equal to 0 is if the numerator is equal to 0. So how about we just say f prime of x equals 0 if and only if the top of this expression equals 0. That's the only way that's possible. So with that, we can go ahead and factor a 2x out, be left over with x squared plus 3 minus x squared, which turns into a, well, 3 times 2x, which is 6x. So this only happens when x is 0. All right, now that we have that, we can draw our sign graph. negative infinity to infinity. First derivative. List our x equals 0, and the fact that the first derivative is 0 there. For sample points, we can just pick negative 1 and 1. So f prime of negative 1. If we go and look at the first derivative here, this entire numerator simplifies into just 6x. And this bottom is always positive. So the only way this fraction, which is 6x over this x squared plus 3 squared, this bottom's always positive. So it's really 6x divided by a positive number. So the only way this entire expression is negative is if x is negative. So because of that, this is negative, and f prime of positive 1 must be positive. So we have negative, positive, which means we have a local min. So we'll conclude by saying a local minimum at x equals 0.